It's our pleasure to have as the first speaker of the conference, Charlotte Kristjansen from Niels Bohr's from Copenhagen, and she will tell us about black holes and integrable boundary states in quantum spin chains.
Okay, thank you very much for the introduction, and thanks to the organizers for setting up the conference and inviting me to come here. It's my first time at the IDD conference series, and it's my first time in Warsaw, and yeah, I'm really happy to be here. So what I will speak about is black holes and integrable boundary states in quantum spin chains. And the talk will be based on some paper that I wrote together with Kristjansen, plus some work in progress. And maybe some of you will recognize my introduction, but for those of you, let me assure that there are some new results towards the end. Okay, so let me start by giving some motivation for this study, first in terms of words, then in terms of images, and then in terms of formulas. So what we want to do is to compute thermal correlators in the ADS-CFT correspondence on the field theory side. And the reason why we want to do that is to, first of all, it can give us some insight into black hole physics, and it also might be a way to make contact with condensed matter physics. But we also had a little bit more technical motivation, namely we had an efficient program for computing one-point functions in defect setups, and we wanted to find out how much of this program would apply to the thermal case. Because a thermal field theory is a little bit like a defect theory. It's a setup which breaks some of the conformal symmetries, in this case, boost symmetry. And our program for computing one-point function in defect setups, it builds on the spin chain description of Enig's also by Mills theory. So to apply this to a thermal field theory would require that we can identify what is the spin chain equivalent of a black hole. We want to find a state which has properties of a black hole in a spin chain, and that's an interesting problem by itself. Okay, so as I said, what I will be speaking about in principle takes place within the ADS-CFT correspondence, which is a common framework for quantum field theory and string theory. And part of that framework is that these two dual types of theories, they share the same spectrum, where the spectrum of the conformal field theory is the spectrum of conformal dimensions. And more importantly, the theories also share the same eigenstates. Here, the eigenstates are good conformal operators, and here, the eigenstates are the energy eigenstates. But what is important for this conference is that both of these sets of eigenstates can be identified with eigenstates of integrable spin chain, and that's how integrability enters this picture. Okay. Now the ADS-CFT correspondence, it comes with a lot of symmetries, and you can of course ask yourself what happens to the theory if you break some of these symmetries. It has both supersymmetry and conformal symmetry, and what happens if these are broken? Does integrability, for instance, still persist? And one way to break the symmetries is to introduce some defect. So it could be a domain wall which separates two regions in space-time where the theory is different vacuum, or it could more generically be some subspace where some of the fields have singular classical behavior, and then that subspace will constitute the defect. And we know what that corresponds to on the string theory side. It corresponds to introducing an extra probe brane in the string theory background, a brane where open strings can end. And we also know what that, well, okay, then that probe brane, it has to intersect our four-dimensional Minkowski space in some subspace, and that intersection then is the defect. And we also know what that corresponds to in the spin chain language, namely such a defect / probe brane can be described as a matrix product state. So it's a state where to each spin orientation you associate a matrix, and then the matrix product state is a sum over all spin configurations, where a certain configuration is weighted by the trace of the corresponding matrices. Okay, that will be more explicit later. And now our idea is that we now want to introduce a temperature in the field theory instead of introducing directly a defect. And again, we know well what that corresponds to on the string theory side, namely it corresponds to introducing a black hole, or more precisely a black brane in the string theory picture. And the question I want to ask and answer in this talk is, what does this correspond to in the spin chain picture? Okay, so let's go to the next level of detail. So as I said, the ADS-CFT correspondence translates a good conformal operator into a string state, and integrability enters because both of these objects get identified with the eigenstates of an integrable spin chain, more precise, an integrable super spin chain. And the eigenstates of such a chain are denoted as U because it's normally expressed in terms of some rapidities, which are denoted as U's. And this relation to the spin chain, it holds in the planar limit of the field theory or the non-interacting limit of the string theory. And the main example is in 4 dimensions where the field theory is n equals 4 super Young Mills. Okay, then the defect setup is what happens if you introduce a domain wall, or more generally a codimension D defect in the field theory, which corresponds, as I said, to introducing a probe D brane on the string theory side. That again corresponds in the spin chain picture to introduce a matrix product state. And that represents these objects in the sense that if you take the overlap between this matrix product state, which is just a state of the spin chain, and an eigenstate representing some operator O, then that overlap gives you exactly the one-point function of that operator. And that is what I want to do for the thermal setup. I want to introduce a temperature in the field theory, which corresponds to introducing a black brane in the string theory. And then I want to find out what state I have to introduce in the spin chain in such a way that when I take the overlap between that state and a beta eigenstate representing a certain operator, then I get the thermal one-point function of that operator. Okay. Okay, so here's just what you need to know about ADS-CFT integrability. It's not much. In the field theory we are considering, we have 6 scalar fields. They're in the joint representation of some gauge group, and therefore I form gauge invariant local operators by taking traces of such operators. And with 6 scalars, I can map these single traces onto states of an SO6 spin chain where the fields are the fundamental representation of SO6 because there are 6 states then. That's kind of trivial, but it's not trivial is that the good conformal operators are then the eigenstates, or can be mapped to the eigenstates of an integrable SO6 spin chain. And their conformal dimensions are then the energy eigenvalues of that spin chain. And again, I use this U to denote the energy eigenstates of the spin chain. Okay, good. Okay, so let me remind you how matrix product states can represent defects in the field theory. So as I said, by a defect, I can formulate a defect as some subspace of my spacetime where some classical fields behave in a singular way when we approach that subspace. And then that subspace will constitute a defect in my field theory. And if I want the resulting setup to be a defect CFT, then I need that these classical fields, they scale as 1 over some x perp, where x perp is some transverse coordinate to the defect. Because only in that way I can conserve conformal invariance or scaling invariance. And there are many examples of such defects which can be represented by matrix product states. There are both examples in this 4-dimensional n equals 4 super Young Mills, but also many examples in its 3-dimensional cousin ABDM theory. And they can have various codimensions, 1, 2, and 3. They can have various amounts of supersymmetry, no supersymmetry, or they could be half BPS, 1/3 BPS, or even 1/6 BPS. Okay, so then I would typically be interested in computing the one-point function of my good conformal operators in the presence of such a defect. And the way I will do it is to take my operator, which is mapped to a spin chain eigenstate, and then in that operator I will replace my scalar fields by the classical expectation values. And that's a process that I can formulate in a convenient way by introducing a matrix product state to represent the defect. So I have the matrix product state must be a sum over all spin configurations of my SO6 spin chain. and each spin orientation has a classical field associated to it. And then I sum over all configurations with some prefactors, which are given by the trace of the corresponding classical field, the product of classical fields. And that works because if I take the matrix product, if I take the overlap between this matrix product state and a beta eigenstate, then this term here will pick out the similar term in the beta eigenstate and replace it by the trace of the corresponding classical fields. And that's exactly what I need to do to compute the one-point function. So therefore, the one-point function can be written as this overlap between the matrix product state, eigenstate, then I have to normalize it by the eigenstate, and then there's this 1 over x perp, which comes out in front. And there's also some field theoretical prefactor that I have ignored. We will not need it in the following. But what you should notice is that this 1 over x perp comes out in front. And that is simply necessary to reflect the scaling properties of the my good conformal operator. Okay, and now it turns out that sometimes this overlap can be computed in closed form, meaning expressed in one formula, just depending on the rapidity variables characterizing this eigenstate. Okay. And when that is the case, we say that the matrix product state is integrable. And by now there exists a criterion for when a matrix product state is integrable, and there also exists a method by means of which you can compute the overlap in closed form when integrability is present. And the criterion for integrability, that's based on the bulk integrability. We have a underlying spin chain which is integrable by itself, this SO6 spin chain. And its integrability means that there exists a series of conserved charges, that is, operators which commute between each other and whose number goes to infinity as the length of the chain goes to infinity. And the matrix product state is integrable if it's annihilated by an infinite series of such charges in the limit where the length goes to infinity. And more precisely, it has to be annihilated by all the odd charges of the spin chain. And that actually corresponds to having elastic scattering at the boundary defined by the matrix product state. Okay, so if you want to be more precise and you also want to extract the overlap, then you have to look at what is called the KT relation. It's a relation, a procedure which has been worked out after many years of various approaches to computing the overlap. And now it's summarized in the fact that you have to solve an equation which looks like this and which is denoted as a KT relation. It involves some object K that you have to determine. And what also appears is a matrix product state, but it's cut open. It's a trace, but you cut it open, so it has two matrix indices. Then there also appears this transfer matrix of the spin chain, which acts on the physical or quantum space of the chain. And then this object K here, it has both quantum indices and boundary indices. And that's the object you have to determine. If it can be determined, then the matrix product state is integrable, and you can extract the overlap from K with from a recursive procedure. Moreover, the overlap always takes the same universal form. I will not go into the details, but this is what it looks like. And let me just mention that this D here, it is the bond dimension of the matrix product state. It's the size of the matrices which enter the matrix product state. Yeah, that's the question, sorry.
Expression. I just asked how K, is that just a set of numbers you put on different sides of the state, but that just is.
Here is for illustrating because, okay. Yes, so once you know this K, then your problem is solved. You can find the overlap in a closed form. Good. Okay, so let's move on to thermal one-point functions. So let's say we don't have a defect. We have introduced a temperature in our field theory background. And again, we want to take our good conformal operators and compute their one-point functions. And now we can already see from scale invariance what will be the behavior of these one-point functions. Because now we don't have this x perp as our scale, but there's a scale which is a temperature. And the temperature has a dimension which is 1 over the length. So the one-point function simply has to scale with the temperature in this way here. And what we're interested in computing is this prefactor BO here. And we will, to begin with, do that at the leading order in the field theory. which means that we ignore all vertices, we just make contractions of propagators. So we need to know the contraction rules for the thermal propagators. And I have written them down here. Well, we need them only for the scalar fields, of course. And the scalar fields are in the adjoint representation of the gauge group, so they are contracted with some delta indices characteristic of matrix models of zero-dimensional matrices. And then there's also a delta function in the flavor index of the field. And then the space-time dependence you get by going to Euclidean space and compactifying the time on a circle of radius beta, which is 1/t. Okay, and then what you need to do is simply to take your good conformal operator and contract fields using this rule here, but you want to do it at the planar level, otherwise you cannot relate things to the spin chain language. Okay, so here's an example. You have an operator of length 8, and you want to contract the fields using this propagator and ensure that the contractions are planar. So this is a possibility. But actually, all these points are taken are the same because there's only one space-time point involved. So I should rather draw the diagram like this, where all the points meet here in the middle, or the single point x is here in the middle. Okay, so now you see that my one-point function, it actually is just a product of identical loops which terminate and start at the same point. So I simply have to find out what is the value of such a loop. And that I get by taking the propagator and identifying its two endpoints. So first, we can notice that if the temperature T is 0, then beta is infinite, and then only the term with m equals 0 contributes here. So m equals 0 is the zero temperature contribution. But I'm interested in the finite temperature contribution, so I will regularize my theory by subtracting that term. Okay. So here is the value of one of those loops, which enter my Feynman diagram, where I have subtracted the zero temperature contribution. Then it's a sum over all modes, except for this zero temperature mode. And that sum is actually finite and can be carried out, and it gives you just 1/12 over beta squared. And there's no time, no space-time point dependence, of course, because I've identified the two ends of the propagator. So I simply get a product of such loops. There are L/2 of them in total. So what my one-point function is, it's this term here to the power L/2, and then I have to count the number of planar contractions in my operator with the contraction rule that I had before. So this is what my black hole state has to do. If I want to define my black hole state as a sum over all spin configurations with some prefactor here, then that prefactor simply has to count the number of planar contractions with the contraction rule that I had before, because the rest is just product of these L/2 loops of identical value. But I can easily construct this number here, the number of possible planar contractions for this field configuration. Namely, it can be given as infinite n value of some matrix integral. That's exactly what matrix models can do for you. They can count the number of planar contractions. So this matrix integral here, it is an integral over 6 different matrices, I run from 1 to 6. Then you have a Gaussian interaction here, which takes care of the contractions, and here is the trace which corresponds to the operator. So my black hole state is simply this sum over spin configurations where the coefficients are given by a matrix integral. So you can say that also in this case, the black hole state is a matrix product state, but in this case it's a random matrix product state. You can also say that this random matrix product state, well, as I explained before, you can only contract identical fields, and you sum over all the flavors of the fields. So what this black hole state actually does is to pick out SO6 singlets, two-side SO6 singlets in your state. And once you've defined this black hole state, then your one-point function is simply the overlap with the eigenstate, normalized by the eigenstate, and then this prefactor, which comes from from the value of the single loop up here. There's also a 1 over square L, which has to do with the cyclicity of the state. But this is the full answer at 1 loop order. And then in the best of all worlds, we will be able to compute this thing here exactly. Okay. So let's look a little bit more closely at this black hole state. So as I just said, it's built from SO6 singlets, and you can construct it recursively. Let's say that you have built the black hole state up for length 2, 4, 6, and so on. Then you can build it for length L by making one singlet contraction. It's between side 1 and side n like this, and then filling out the internal part and the external part by smaller black holes. So this is a way of recursively constructing the black hole state. You can also say something about its integrability properties. So it's of course again a state of the SO6 spin chain. And as I explained, we can check for the integrability of the chain by checking if the odd charges annihilate that state. And the odd charges, in particular the first one, you can construct easily from the Hamiltonian of the spin chain. So if you write the Hamiltonian of the spin chain in this way here as a sum over Hamiltonian densities, then the first conserved charge is given at this commutator here. It's something very concrete. You can apply it to something which is also very concrete, namely the black hole state, and you can see whether the black hole state is annihilated or not. And you find that it is not. So it means that this black hole state is not integrable. And therefore, we cannot hope to find these one-point functions in a closed form. And that's kind of expected. You don't expect a black hole state to be something integrable. It's more or less by definition, it's something chaotic. So you have to study it by other means. So let's see what other means are available. Okay, first of all, let's do a warm-up exercise. Let's try to figure out what would be a black hole state in the SU2 spin chain, because it's simpler than the SO6 one. So we would build it by analogy with the SO6 case. So we'll build it from singlets, or two-side singlets. But two-side singlets in SU2 are of course different from singlets in SO6. In SU2, a two-side singlet simply looks like this. And again, we can build our black hole state recursively. Now, instead of having identical flavors for the field set side 1 and the 2n, we now have a sum with the epsilon symbol. That is, we have this singlet here as side 1 and n, and then that corresponds to one arch in the picture from before, and then you put lower black hole states under the arch and beside the arch. That's the same type of recursive generation of the black hole state. Again, the black hole state can be constructed as a random matrix product state. So if you write it as a sum of all spin configuration, then your wave function components here can be given by the large n limit of a certain matrix integral. But this time, the matrix integral, it has to be over Grassmann valued matrices, because otherwise you cannot get this antisymmetric contraction to work up here. That would simply kill the trace unless you say that the trace is built from Grassmann variables. Okay. So this SU2 black hole state, let me say it has nothing to do with thermal correlation functions, because this SU2 singlet, it does not appear when you do thermal contractions in the SU2 sector. So it's a toy model. But you can study it more easily than the SO6 spin chain, of course. So what you can do, first of all, is to try to see how it behaves under a translation by one side. And you find that if you act with it with the translation operator, then you get minus the black hole state coming back, which means that it has momentum pi. You can also check for integrability. And again, you find that the black hole state is not integrable, which again is not really a surprise. So we cannot expect to find this overlap in a closed form, but we can try to study the state in various other ways. We can look at its entanglement entropy, thermalization properties, and maybe its preloop complexity. Okay. So let's first look at the entanglement entropy, the relative entanglement entropy. So it's a quantity that you can define if you have a quantum system with a Hilbert space, which is easily split into 2 or more parts. And that's, of course, the case for a spin chain. You can easily cut it into two parts and have two different Hilbert spaces of the same type. So if the density matrix for the full system is rho, and your two subsystems are A and B, you define a reduced density matrix rho A by tracing out the Hilbert space B. And then you define the relative entropy of A relative to B as trace rho A log rho A. And that's something you can really easily compute for a spin change state. You start by normalizing the state, and then you write it in this way here, where these i's and j's are the obvious bases in the two subspaces of smaller spin chains. Then you get some matrix here, M, which is typically not quadratic, and your reduced density matrix is simply just M times M dagger if you want rho A, and M dagger times M if you want rho B. And then you can diagonalize it and find the entanglement entropy. So we want to do that for the black hole state, and we want to contrast it to an integrable state, which is similar. And the one we will take is one which is a so-called valence bond state, where there's only some correlation between nearest neighbors. So it's built from arches in the diagrammatic picture, which are just in a long row, no arches below other arches. So it's a wave function which is simply a product of epsilon factors. And then we take this state, and we can also subtract its one-side translated version, because then we get something which has momentum pi, and it gets even closer to our black hole state. So we want to contrast the entanglement entropy between these two types of states. And this is what we find. So this is in relative entanglement entropy for the SU2 case, for the black hole state and the integrable state that I just introduced. So the length of the chain is 20, and this is curly L is the length of the piece that we cut out. So you see there's a big difference between the integrable state and the black hole state. So the integrable state, it has in the infinite L limit a constant entanglement entropy, saturates at the value 2 log 2, whereas the entanglement entropy for the black hole state, it's not constant, and also doesn't grow with the volume of the state. It grows, as we will see on the next slide, logarithmically with the length. So you can, this saturation value you can actually argue for analytically, but that's not really what interests us. What interests us is this logarithmic behavior for the black hole state. Okay, this is the same curve again for the black hole state, and now it's fitted to this functional form of the relative entanglement entropy. It's a formula which has been derived by Cardio and Calabrese in the continuum CFT language. And it involves the central charge of the underlying model and then some universal constant C1 here. And we can try to fit those constants to our data. And what we find is, as in some sense, an effective central charge, which is something like 1.2. And this behavior here is characteristic of the ground state of a critical system with central charge C. So we find this interesting, but we don't know exactly how we should interpret this effective charge central charge that we find in our setup. But it's definitely a very different behavior from the integrable matrix product state case. Okay. Here's some results for the SO6 case. Here the length of the chain is only 10. It's of course more complicated to calculate the entanglement entropy here because there are many more contractions. And again, we compare it to the entanglement entropy for an integrable state, which consists only of arches which are not beneath each other. And this time it's built from delta function and not epsilons, because it has to mimic the SO6 singlet. And also, instead of taking 1 minus the translation operator, we take 1 plus the translation operator. So we get a state of momentum 0. And you see again the same picture. The integrable matrix product state has an entanglement entropy which saturates at some value. It's actually log 12 in this case, and you can argue for that again analytically. But what interests us is this logarithmic behavior for the black hole state. We don't have as good statistics as before, but if we just naively make an estimate for the central charge, then we find that it's 4.5. Again, we don't really know where that number comes from, how we should interpret it, but of course we would like to find out. Good. Okay, so we can try to study these black hole states in other ways. We can try to look at their thermalization properties. And we will do that by making use of what is known as the eigenstate thermalization hypothesis. It's a hypothesis which says that the time average expectation value of some operator, which is local, and well, in a state which is sufficiently generic, is actually given by the expectation value of the operator in the thermal ensemble. And that somehow builds on the assumption that for a sufficiently generic state in a model without too many degeneracies, then this time average expectation value is just given by the diagonal matrix elements. That's the eigenstate thermalization hypothesis. And if this relation is fulfilled, then the state thermalizes at a certain temperature given by this expression here. And that's something you normally expect for chaotic but not integrable systems, because for integrable systems there are of course many other conserved charges than the energy, which is related to the temperature. But nevertheless, we will argue that our black hole state seems to thermalize at infinite temperature. Okay, and to do that, we will compute this this object here analytically, and then we will compare with numerical experiments where we determine this sum up here. And this object we can determine analytically. We do it here in the SO2 spin chain. So at infinite temperature, then the then rho is simply a flat distribution over all states. And since our black hole state consists of singlets, then this rho in the infinite temperature limit is simply a projection onto singlet states. And this we can write as 1 over the number of singlets times some projection operator. And the number of singlets is just the number, the Catalan number, because the recursion relation that I showed you earlier is simply the recursion relation for the Catalan numbers. And the projection operator you can get using some group theory. Namely, you can write it as an integral over a tensor product of L group elements integrated with a Haar measure. And if you then parameterize the SU2 group element in this standard way with the sigma matrices, then this just becomes an integral over S2. So if you do this integral, well, okay, then this implements the projection on a singlet state. If you take the trace, then you get the number of singlet states and you reproduce this Catalan number from before. Then as our operator here, our local operator, we will use what is known as the emptiness formation probability. It's simply this operator here. So it's 1 if there are small n states, spins next to each other which point up. And otherwise it's 0. So therefore it's a probability. And it's called emptiness because originally it was defined with a minus here, and spin downs were denoted as empty states at some point. Okay, so we have a concrete expression for the projection operator. We have a concrete expression for our operator. So we can simply compute the trace of the combined action of the two. And it's a group integral, which turns into an angular integral. Here's a small n coming from the emptiness formation probability and the rest here. We've taken the trace and we simply compute this integral and find some combination of factorials. And in this expression, we could take the limit where L goes to infinity, but n over L is kept fixed, where n with a number of identical spins. Then you find exactly what this function f here looks like. And yeah, it's Stirling's formula, basically. So we know what our prediction for the time averaged expectation value is, and we want to compare it to what we get in the diagonal example. And that is something we compute numerically. And here's what we find for the SU2 case. So the solid curve here is the analytical formula, the prediction. And then we have done it for the integrable SU2 spin chain. It's the blue points here. And you see that at least the qualitative features of the curve seem to match quite well. So it does look as if the black hole state thermalizes at infinite temperature. And maybe you find that's a bit strange because the underlying model is integrable. And the eigenstate thermalization hypothesis is supposed to work mainly for chaotic systems. But then we've tried to perturb this integrable Heisenberg spin chain with a next to nearest neighbor term of a size that makes it chaotic. And you see that the picture doesn't change much. This is the violet points. So we take this as an expression for the fact that actually the thermalization properties are not really defined by the underlying spin chain, but by the black hole state itself. So the black hole state has some chaotic features, and it's the black hole state which thermalizes at infinite temperature. Here's the similar curve for the SO6 case. Again, the data is more sparse. The length of the chain is only 10. But you see again that the qualitative features look very good. Again, you have this curve you can find almost analytically, not exactly, but you can find it by a saddle point approximation. Actually, you can find it for SO2A plus 1, so A equals 2 is our case, and A equals 1 is twice the SU2 case. So also in this case, which is the physical thermal one-point function situation, there seems to be a thermalization of the black hole state at infinite temperature. The last thing I want to say something about is the Krylov complexity. So it's a complexity measurement for states. So the way you compute it is that if you have some normalized state, which in our case would be the black hole state, then you define the Krylov space of order k as a state is spanned by the state you get by acting with the Hamiltonian 1, 2, 3 up to k minus 1 times. Then you use what is known as a Lang's algorithm to find an orthonormal basis for this space. This algorithm works in such a way that your Hamiltonian becomes straight diagonal, that is hopping like in that space. And then you study the time development of your state in that basis and find the Krylov complexity as the average distance from the initial state that your state psi has moved in t time steps. And you can also integrate over time, average over time if you want. Okay, here is very fast the results for the black hole state and the integrable state in the SU2 case. So the further the state has moved from its integrable value, the more complex you would say the state is. So here, although the statistics is not very impressive, you can see a clear qualitative difference between the two types of states. The black hole state has a Krylov complexity which grows faster and saturates at a higher value than the integrable boundary state. And yeah, I said the statistics is not so good, but well, actually we have available only 69 singlet states for the black hole. But I think the qualitative picture is clear. Okay, and that takes me to my conclusion. So what we have done is to identify a spin chain boundary state, which we call a black hole state, which encodes the leading order thermal one-point functions in AJ-CFT. We've studied its complexity properties and found some curious results, namely that its relative entanglement entropy grows logarithmically and that it thermalizes at infinite temperature. What we would really like to do is, of course, to understand the meaning of this central charge that we extract from the entanglement entropy plots. We would maybe like to do something more for the full N=4 super theory, look at the strong coupling behavior where the black hole really appears. But there are also many things you could consider from the condensed matter perspective. You could introduce black hole states in other quantum many-body systems, and you could study quenches with black holes as quench initial states, as people studied quenches with matrix product states as quench initial states. So yeah, hope to report on that in the future, and thank you very much for your attention.
So thank you very much. Are there any questions?
Yes, thank you so much for the nice talk. So my question is about holography. Have you tested holography, say for how easy it is to compute the ground state one-point function, for example?
Ground state
Of this matrix product state with ground state of the spin chain.
But
Then maybe compare with.
we are.
No, it's difficult.
Well, we're computing thermal one-point functions, so we are.
Yeah, but you have the the black hole product state, and then on the other hand, you have some beta state, right?
Yeah. Yes.
And then how about taking the ground state?
With all the spins.
Yeah.
But
It's very simple.
It will not work because it's not a singlet.
Ah, I see.
The
You
black
cannot
hole
test
state is-
holography for this simple case. So how do you test holography?
Well, I'm just at 3 level, so for the moment I cannot really test holography. What I can test is have the appropriate scaling, and I have.
Right.
Yeah.
I see. Thanks.
But of course, it would be a dream scenario if you could somehow bootstrap this to higher loop orders as it was possible for the matrix product state. And then, of course, eventually you could maybe say something about strong coupling. But we're not there yet, and we don't really know how that bootstrap could work since we don't have integrability.
Also, strong coupling, I mean, you should have some open string in some black hole background, right?
Yes.
No, not open string, some kind of, how would you compute one-point functions in?
Well, you basically have a string which drops from the boundary and disappears into the black hole. We have to look at that process. Yeah.
Okay, any other questions? Maybe also online, you can type your questions if you want. Then for now, I have maybe one question. So you compute everything within using n equals 4, but in the end, at least to my eye, it looks like you don't need like supersymmetry or something, but how much does rely on supersymmetry or just on integrability?
No supersymmetry for the moment.
Okay.
And I think you could take any spin chain or quantum many-body system and define a similar state and study its properties. And it would be very interesting. Yeah.
So most of the properties you showed seem very dependent on the state and not on the Hamiltonian. But to do Krylov, you had to choose a Hamiltonian like a Heisenberg or something like that, right? How important is the Hamiltonian you use to evolve the state for Krylov complexity?
But Krylov complexity or?
For Krylov complexity, yeah.
I think it didn't look that different, actually.
Sorry?
It did not look very different if I perturbed the SU2 Hamiltonian, for instance.
Okay.
And also not if I perturbed the SO6. But I've changed our short, so yeah, should be studied.
So if you would add, for example, the next loop in the Hamiltonian and act in the same state, wouldn't...
you would still see that the complexity of the black hole state would be much bigger than the integrable state.
Okay, nice. Yeah. Thank you.
For the length that we have considered. Yeah.
Yeah, so possibly naive question, but just the interpretation of this as a black hole state comes from n equals 4 and thermal and stuff. But so if you just consider a generic quantum many-body system,
yes,
what is it that characterizes this as a black hole state? Or
that it's built from two-side singlets.
and what?
So you need some kind of underlying symmetry, which is.
Is there a sort of physical interpretation of why that's an interesting thing to compute for a general quantum many-body system, or?
Well, I would say this mainly this thing with the entanglement entropy, that it gives some effective central charge. That could be the signal of some underlying CFT that we don't really know.
So there's some hidden.
Yeah.
Oh, we have a question online
Ah.
from Dan Thompson from Swansea.
Yeah.
So he's asking to look forward. Do you anticipate that the spin chain could provide a platform to investigate page curves, for example?
Well, this spin chain, it pertains to the case where you work on Euclidean R4. But to study page curves, you have to compactify on a screen, which gives you another scale, which allows you to study page curves. So not immediately. That's the answer. Yeah.
Okay, then let's postpone further questions to the break, and thanks, Charlotte, again.